Hello, welcome to another A-Level Maths video. This is a Pure Maths Year 2 video where we're starting to look at Chapter 2 of the textbook, and in this video we're going to look at Section 2.1, which is all to do with the modulus function. So have you seen the modulus function before? You might have done. Well, anyway, there's a definition on the screen here which we're just going to look at together. So the modulus of a real number is the size of that number ignoring whether it's positive or negative, and we write it with little vertical lines around it. So let me show you some examples of what I'm talking about here. If we had, for example, the number -2, then the modulus of that number -2, we'd write these vertical lines about it, would be 2. And the reason for that is because it has a size of 2, but we just ignore the fact that it's a negative number. Okay, so the size of that number -2 is 2, so the modulus of that number -2 is 2. Let's have a look at another example. Let's say the number 17. What's the modulus of the number 17? Well, that is still just going to be 17. So the size of that number 17 is 17. It happens to be positive, but we don't really care about that when we're talking about moduluses here. Okay, got the idea? Let's just do one more just to make sure we've got what's going on here. Let's say we've got a slightly more complicated number, something like -10/3, let's say, and we want to find the modulus of that number. So the modulus of that number would be 10/3, and the fact that it's negative, we don't care about that, particularly for the modulus. Okay, quite a simple idea, I hope you agree. Now we'll look at something very slightly more complicated before we sort of go too much further with this, because it's not just going to be how big is this number. We need to be able to kind of deal with this in the context of other functions as well. So on the screen here we've got an example which we're going to look at together. Let's see if I can get some space on my pad here to do that with. So we've got some function here, f of x, which is defined to be 10 minus the modulus of 6 minus x, and then we're allowing all real numbers to be the inputs to that function there. Okay, so we've been asked to find first of all f of 8. So let's just take the number 8 and we'll substitute it into the function here. Okay, so you can see how this is going to work here. We've got 10 minus the modulus of 6 minus 8, or the modulus of 6 minus 8. 6 minus 8 is of course -2. Okay, and the modulus of -2 is going to be 2. So we end up with 10 minus 2, and the answer there is 8. Okay, got that? Let's just see if we can quickly work out the f of the -8 here. So if we have an input of -8 here, we have 10 minus the modulus of 6 minus -8. Okay, that becomes 10 minus the modulus of, well, 6 minus -8 is 6 plus 8, which is 14. And the modulus of 14 is simply just 14. Okay, doesn't matter that it's positive, we just sort of say that the size of that number is 14. So we end up with our answer here of -4. So f of -8 is going to be -4. Got the idea? All right, let's see if you can get on with one yourself then. So there's a question on the screen. Pause the video and then restart once you've got your answers. Okay then, let's just see if you agree with this then. So here's our function here, g of x equals the modulus of 4 minus x squared. If our input number was 1, then we're going to end up with the modulus of 4 minus 1 squared. 1 squared is of course just 1. So we just end up with the modulus of 4 minus 1, which is 3, and the modulus of 3 is 3. So g of 1 equals 3 here. Okay, what about if our input number was -3 then? So g of -3, well, that's going to become the modulus of 4 minus -3 being squared. -3 squared is of course +9, so this becomes the modulus of 4 minus +9, which is the modulus of -5. And the modulus of -5 is just the size of the number, ignoring the fact it happens to be negative, and that is the number 5. Okay, so quite an easy thing to do so far, I think, if you understand that the modulus is really just the size of that number. However, there are times when we're going to need a more formal definition of the modulus, and here's what I've got on the screen here. So if you think about it, that modulus didn't really have any effect on any numbers which we put in which happen to be positive numbers. So for example here, the 17 here, when we took the modulus of the 17, it just became 17 again. So positive inputs just give us exactly the same number as the output. However, when the input was negative, we had an output which was positive. And the way it became positive, you can think of it as taking this negative number and multiplying that by -1. So here, for example, we can take the -2, multiply it by -1, and it gives us the +2 as the output here. Put that in brackets to make that really clear what's going on. Yeah. Similarly here, this negative input, if we take that negative input and multiply by -1, we get that positive output here. And that all leads to that result which is on the screen there. So if we have an x value, an input value which is positive, then the modulus doesn't really do anything. If we have an x value, an input value which is negative, then we can think of the modulus as multiplying it by -1 to make it positive. And it's this more formal way of thinking about the modulus function which is going to help us understand how the graphs which involve modulus functions behave here. So let's see if we can sketch a graph here which involves a modulus function. So I'd like us to see if we can sketch the graph with the equation y equals the modulus of 3 minus 2x. I'm actually going to get the graph plotter here to help me out with this. So the modulus of 3 minus 2x here, what's that graph going to look like? Well, what we could do is we could start off by looking at what the graph of 3 minus 2x without the modulus looks like here. I've drawn it there as a little dotted line. So that's the graph of 3 minus 2x. Now, of course, the modulus, if the output is already positive, so if the thing inside the modulus is what I mean by that, if that thing inside the modulus is already positive, then the modulus doesn't have any effect. So that means that the parts of the graph which are already positive there, which are the parts above the x-axis, that is all going to be exactly the same for the modulus graph as it was for that original graph. The bits where the output is negative, so the bits down here, the modulus is going to have the effect of multiplying by -1. In other words, we're going to be looking at the graph minus the 3 minus 2x here. And do you remember that transformation from your previous work here on graph transformations? It's a reflection in that x-axis. So overall, what we're going to have here in total, altogether, is we're going to have that graph there. The part of the original graph which was already above the axis is just going to stay put and nothing's going to happen, and then the part which happened to be below the axis is going to be reflected above the axis there. Okay, so there's the method on the screen here. If we have a graph which is y equals the modulus of some function of x, then all we've got to do to sketch it is we've got to sketch the graph of that function of x, and then any part of the graph which is below the x-axis will reflect it to be above the x-axis. Let's see how you get on with one yourself. Pause the video in a second, sketch that graph with the equation y equals the modulus of 4x plus 3. Okay, let's have a look at this one here. So this is the graph that we want, y equals the modulus of 4x plus 3. So the first thing we could do is we could just draw ourselves, maybe as a dotted line here, the graph of 4x plus 3 without the modulus. Well, that's going to have an intercept here at 3. It's going to have a gradient of 4, so quite steep, and I'll draw it like that. So we're only doing a sketch, of course, so that's what we got here. So the part of the graph which is already above the x-axis, the modulus is going to have no effect on that whatsoever. So that part there, I'll put that in as a nice solid line now, and that is going to be, that little branch of it has got equation just y equals 4x plus 3. The part which is below the x-axis here, that's going to be reflected above the x-axis when the modulus happens here. So that part which was down here, now been reflected above here, and that branch of it there has equation y equals minus 4x plus 3 like that. Okay, so the whole thing all together is the graph of y equals the modulus of 4x plus 3 like that. Did you agree? Okay, So there's going to be a lot more on sketching modulus graphs later in the chapter, but we do need to know how to do these particular types now, because we're going to now look at another kind of thing that we might need to do with modulus functions. We may have equations which have modulus functions as part of them, and we need to be able to solve those equations. So the equation on the screen here, we'll have a look at this one together. We've got the equation there, and what I'd like to do is see if we can use a graphical method to help us with this. So the first thing I'm going to do is I'm going to see if we can get that graph of the modulus of 3 minus 2x back up here, because we did this one earlier on. We're also going to put on here the graph of y equals 4x. Okay, nice straight line there. Now you should be able to sketch these. You don't necessarily need the technology to help you with these. The way we're going to solve the equation then is we're going to look for the intersection point. We're going to look for the x coordinate of that intersection point. So we just need to be aware which branch of the modulus graph we're on here. So were we on the original branch, or were we on the reflected branch because of the modulus function here? So let's remind ourselves about that one here. Remember, the original 3 minus 2x was this line down here, that dotted line there. And when we did the reflection, or sorry, let me say that again, when we sketched our modulus graph, we had that part there which was unreflected and that part there which was reflected. So what we're doing here is we just need to be aware that we are looking for where the unreflected part of the graph, which is just the 3 minus 2x, is going to equal 4x here. Okay, let's transfer to my drawing now here. So I've just done the sketch of what we've just been looking at. And so I just need to be aware that this branch of the modulus one here, that was the one where we had the reflected part. So that's y equals minus 3 minus 2x here. Now, I don't really care too much about that for this situation, because I can see that my intersection point is not on that branch there. What I do care about is I care about the fact that my intersection point that I'm looking for here is on the unreflected part of the graph, which just has equation y equals 3 minus 2x here. So let's see how we're going to find that intersection point. We just need to set up the equation here. 3 minus 2x equals 4x, and that's a relatively easy one to solve. Add 2x to both sides, and then divide both sides by 6. And we're just going to end up with x equals a half there, and that is our only solution to that modulus equation. Okay, to get the idea. So if you want to solve a modulus equation, or an equation which involves a modulus, I strongly recommend that you use this graphical method to do it. Here's a question for you to have a go at. So sketch the two graphs on the same axes there, and then find the two roots of the equation that's given there. Okay, over to you. Okay, how did we get on with this one then? So I've got the graph plotter to help me with this one. So your sketch should have looked a bit like this here. The modulus graph here, the modulus of 4x plus 3, that was looks a bit like this. And our y equals minus 2x minus 1 here is this line. And you can see there are two intersection points here. Now, this is why the graphical method is really useful, because we can see those intersection points and we can see exactly where they are. And therefore, we know that we are looking for where the 4x plus 3 equals minus 2x minus 1 is going to be one of those intersection points, because that's going to relate to where the modulus had no effect, essentially. So the 4x plus 3 just stayed as a 4x plus 3. But also, we're going to be looking at where minus 4x plus 3 in brackets like that equals minus 2x minus 1. That's also going to give us a solution as well. And we got that by recognizing that there was a root on the unreflected branch and a root on the reflected branch. There was intersection points there. Okay, let's just very quickly go through these. These should be fairly simple equations to solve. Add 2x to both sides here. You get 6x. Subtract 3 from both sides. I think we get minus 4 here. So that leads us to x equals negative 2/3 as one of the solutions to the equation. And then for this one here, let's just expand out the bracket first of all. So minus 3 minus 2x minus 1 on that side. Add 4x to both sides. We're going to end up with 2x on there. Add 1 to both sides, negative 2. So that leads us to the second root of the equation, which is x equals negative 1. And if we quickly return to the graph plotter here, we can see that, there we go, x is -1 is one of the roots here, and then there we go, that's the decimal version of -2/3 right there. So we've got it right. Okay, so there we go with this section of the chapter then. We have here lots of stuff to do with the modulus function. We've introduced ourselves to what it means, how to sketch graphs, and how to solve equations. All right, more on this stuff coming later in the chapter, but that's it for this video. Please do consolidate by looking at exercise 2A of the textbook, and I'll see you again next time.